All right, so today's lesson is focusing on depth perception, which again is the ability to see objects in 3 dimensions, although the images that strike the retina are 2-dimensional. This allows us to judge distance. We talked about the visual cliff on the last screencast, but just to review quickly, in the 1960s, sensation and perception psychologists wanted to figure out whether or not depth perception was innate. It was something we were born with, or if it was a learned ability. And they did find, after testing infants and young animals using the visual cliff, that it was something that we were born with. However, it was enhanced with experience. There are different cues that we use to help us perceive depth. Binocular cues are depth cues such as retinal disparity and convergence that depend on the use of 2 eyes. Bi, we know, is a prefix that means 2. So that should help you. It also is helpful to remember that there are 2 binocular cues. When we talk about monocular cues, the use of 1 eye, I think there are 8. So you have to remember the 2 different binocular cues that allow for us to perceive depth based on the use of 2 eyes. One of them is called retinal disparity. And the fact that we have 2 eyes about 1.5 inches apart, well, the images that are cast on our retina are compared, and our brain actually computes the distance between the retinal images. And the greater the disparity or distance between the 2 images, the closer the object. 3D movies oftentimes mimic normal retinal disparity. We wear 3D glasses that allow the left eye to see only the image in the left camera and the right eye the only image of the right camera. So 3D movies, we do know, enhance depth perception. This next slide you see here helps understand the difference between retinal disparity, and it's the finger sausage, the floating finger sausage experiment or test. If you were to peer across the room and you hold your 2 index fingers out in front of you, right in your line of vision, but you don't focus on your fingers, you are focusing on the back of the room, and you move your index fingers together, it actually creates a floating finger. And I know it's hard just listening to me and not watching me model it, but the little picture up in the corner here is what should happen. But again, you're not focusing on your fingers, you're looking past them. The second binocular cue is called convergence. This is another binocular cue to help you perceive depth. And it's basically the extent to which the eyes move inward when looking at an object. The greater the inward strain, the closer the object. So this is kind of a funny little illustration of a man crossing his eyes, but we truly know that our eyes do converge. So that should help you with remembering the binocular cue. You need 2 eyes to create an inward strain. And again, the greater the inward strain, the closer your eyes are together, you know the closer the object. If you just hold your finger out in front of you, your index finger, and you move it closer to your nose, you know that your eyes go crossward at some point. And the further out you hold your finger, the less inward strain. All right, so moving on to monocular cues. These are the ones that I think get a little bit tricky, and is going to be it's something that we are going to have you do an assignment on to help you really process and understand the difference of the monocular cues. A good way to really understand monocular cues, which are depth cues that are available to 1 eye alone, either your left eye or your right eye, is by looking at art. And on your assignment that you're going to do, you're actually going to upload some kind of landscape image into Notability, and you're going to identify, highlighting, numbering, whatever system you want to use, where the depth cues we talk about are located in your particular illustration or landscape picture. So here we go. First one that we're going to be talking about is relative size. So in judging the distance, the one that casts a smaller retinal image is perceived as further away. So using even just one eye alone, you know that the yellow circle in the very front, the yellow ball, is giving a bigger retinal image. The blue one in the back casts a smaller retinal image. So relative size helps us perceive depth. The smaller the image, the further away we perceive it. Excuse me. You can use another example like when you're driving. Distant pedestrians will appear smaller, which also means that the small-looking pedestrians, children, might sometimes actually be misperceived as further away than they actually are. So you have to be careful with that. Another example is what's called interposition. And this is an illusion, this picture, which messes with your ability to perceive depth because the woman riding the horse is being blocked partially by trees. Now, if one object partially blocks our view of another, we perceive it as closer. Thus, we know which is further away based on what's blocking our vision. So this painting purposefully confuses the figure and ground, which we talked about, figure ground illusions earlier, by interposition. In relative clarity, we know that light from distant objects pass through more atmosphere. So we perceive hazy objects as farther away than sharp, clear objects. So you can see in this illustration, the mountains in the back are way more hazy than the landscape right up in front of the fence. You can see more detail. And so we know that that is closer to us than the hazy fogginess. Sometimes you have this when you're driving as well, because the objects that are further away are hazy and they're not as detailed, where the closer up objects are sharp and clear. With texture gradient, you see a gradual change from a coarse, distinct texture to a fine, indistinct texture, and that signals increasing distance. So objects far away appear to be more small or smaller and more densely packed, and you can see this for sure in the illustration on the left. The more densely packed the image, the further away we perceive it. Relative height is another monocular cue. Relative height is when we perceive objects higher in our field of vision as further away. So on the left is the vertical line in the diagram below longer, shorter, or equal in length to the horizontal line. It's kind of a little illusion test for you. When you look at the figure ground illusion on the right, we oftentimes find that the white portion is the sky and the atmosphere, and that is the ground. That's the background, where we perceive the black as being the figure and closer up, almost like buildings. And because it's higher in the white is higher in our visual field, we will perceive that as being further away. With relative motion, as we move, objects that are actually stable may appear to move. If while riding in a car you fix your gaze on some objects, say the house, the objects closer than the house, which is your fixation point, appear to move backward. The nearer the object is to you, the faster it seems to move. And this holds true when you look out your window while you're driving. Your brain uses the speed and direction cues to compute the object's relative distance. Linear perspective. Parallel lines such as railroad tracks or roads, they appear to converge with distance. So what you see here is a staircase, and the more the lines converge, the greater the perceived distance. That one's pretty easy. You see that a lot in artwork. With light and shadow, nearby objects reflect more light to our eyes. So if you're given two identical objects, the dimmer one seems further away. This illusion can also contribute to accidents, as when you drive and it's foggy out or snowy out and the vehicle in front of you seems further away than it actually is. So artists use shading a lot to produce a sense of depth that's consistent with the assumed light source. Light and shadow. With relative size and distance, we talked about this before, but you can we know the size of elephants, and this is like an antelope or a gazelle of some sort, and we know that elephants are generally larger animals than gazelles. And so because of the relative size there, we know that the elephant is further away than the antelope, and that this creates a perception of depth. Now, I want to show you guys this illustration right here because you really can understand what I'm expecting of you guys in your assignment by looking at this piece of art. You can look at a lot of the different monocular depth cues and use it to help you with understanding. So if you do relative size, for example, okay, we understand that these individuals are closer to us because these individuals are way bigger than these individuals right here in the canvas. You could also use relative height as an example. These individuals are perceived as further away because they're higher up on the canvas. Just like these buildings right here are higher up on the canvas, and we perceive them as being further away than these buildings that are closest to us and are lower in the canvas. Although we do see that the roof is higher than here, it still starts right here on the lower part of the canvas. Inner position. We know, let's see, what can we use as an example? I know that this part of whatever structure is right here is further away than this man because he is blocking my view of this structure. You could also use, for example, where's another one? You could use any of these boats that are blocking the view of the houses behind because the masts are blocking the view of the houses. Let's just use linear perspective. You can see how this road right here, it converges and it gets smaller on the canvas. Whoops, I just hit the next one. So because it starts out wide and it narrows, we know with linear perspective that this is further away. In terms of like texture gradient, we know that densely packed, fine objects are further away. These are definitely densely packed. It's more spacious over here. Same with the clusters of individuals. Even with relative clarity, you can see this is way more hazy and everything is more distinct and clear and fine closer to the front of the canvas here. Light and shadow, you can see that to be in any of the shading with any of the buildings. You could use multiple examples for this. So I hope this helps you understand not only what the difference is between binocular and monocular cues, but how to use this as an example for your homework assignment. When you open up the document and you put it into Notability, you need to define the different monocular cues, but then you somehow need to demonstrate where they're located, either by highlighting, numbering, explaining in your written portion where your monocular cues are in the piece of art that you have chosen. It can be a picture, a photograph, any kind of landscaped image. Really, there's no right or wrong picture that you choose as long as you can really find all the different monocular cues within it.